Hello, John.
Hello. Thanks for having me.
Welcome to the Power Pulse podcast. It's wonderful to have you here.
It's a unique opportunity to go from being a listener, a little more difficult being on this side of the mic,
good.
But
So
I look forward to it.
You did listen to the first season then?
Yes, of course.
Oh, good. Let me start by asking, you're in a band, I hear.
I am.
Tell me more. What kind of band?
Yeah. So, unfortunately, not a jam band, right? Not a rock band, but rather, I play euphonium of all things, right?
Oh, wow.
So it's a brass instrument that looks a little bit like a miniature tuba.
How did you get into it?
I got into it because when I was much younger, a little bit thinner and with brown hair, I used to play a lot when I was a kid and when I was a student. And then I stopped for 30 years. I moved to Switzerland and realized when I moved from the city out to one of the villages that I was looking for a way to integrate myself better with the local community. And I heard the band playing and I'm like, oh, cool. So then I chased them down and I said, do you need a trombone player? And they said, no, we have too many. So I said, faking it a little bit, do you need a euphonium player? They said, that we could use. So
it's a famously hard instrument to master, isn't it?
To master, yes. Notice I don't quite claim mastery, yes. But I enjoy it very much and play it every week with the Kirchberg Harmony.
Oh, wonderful.
Yeah.
That's great. Have you invited any of your colleagues around to have a listen?
I have.
What's the feedback?
Super feedback, but they were well primed, right? So.
Moving swiftly on to business.
Okay.
We're serious now. Tell me what our grid interface is. That's what I want to know for this episode.
Okay. Yeah. So first of all, let's just try to adopt an idea of what is an interface, right? So an interface is essentially when two systems meet each other and need to connect in any way. And we have interfaces of two types in the electricity grid. One is an electrical interface, which are the definitions of how copper typically connects to other copper in a safe manner and allows things to plug in and move energy in a safe and effective manner. Some of this was discussed in some of our products and technology in the first season. And for our listeners who want to catch up a little bit, what would be an electrical interface, it would be what's the standardized or defined method for connecting a charger from a phone to a phone, right? Which 10 years or so ago was every phone had its own unique charging mechanism and you had cords all over the house, depending on where you were. That's largely been replaced now by a standard USB interface, right? Yep. So that you buy a phone and you don't have to worry about the charger, right? And so that's kind of the goal of any modern industry as it matures, which is to try to find efficient ways for systems to talk to systems. I mentioned the electrical interface or the power interface. In grid automation, what we deal a lot within is the information, communication, and software interfaces. And these are the methods that two digital systems use to talk to each other to exchange information. And one could ask, why bother to specify this? Well, it would be a bit like building a house and showing up on site and wondering why the window doesn't match up with the door at the same. It's because there's a certain level of agreement of technologies and methods that when done a priori make it a lot easier to connect systems together. And this is something that we work on very hard in Hitachi Energy to make sure that our software systems can talk to other systems very cost effectively and very, very easily. And it's something, quite frankly, that our customers do and the whole industry looks for, because nobody derives value from showing up on site and writing custom code to get one piece of software to talk to another.
Right. So you've told me what they are, and you've touched upon a little bit why they matter. Could you tell me a little bit more about that? Yeah,
sure. It's a cost-saving and time-saving measure for all parties involved, right? So innovators want to spend their time writing better software to do something interesting, to do something useful for the customer. And they want to be able to deploy this on a framework that talks with another system. Imagine that you were writing an app for an iPhone, and as soon as you finished writing the app, you had to say, okay, now how do I get the phone to turn on for this to display? Nobody writing an app for a phone has to worry about this. They use a standard application interface that they're told, make the data plug in here, and then it magically not magically, but in a standardized fashion, we'll make it work. And that's the same reason that interfaces matter for getting software systems to talk to each other, so that systems can talk and they can plug in and do it quite cost effectively. It also impacts stability, because anytime that you are connecting two systems together and you're doing plumbing to tie the systems together on site, you're likely to make a mistake. But if you really test and reuse the same method, the same connectors for plugging two systems together, the likelihood that something goes wrong greatly reduces, and the reliability and the availability of the system for our software, for example, to keep the grid running, ends up with a much higher reliability piece of software.
And this is not something that only Hitachi Energy does?
No, and in fact, it's extremely important that everybody does it, but everybody does do it because
it's not a product, it's a service.
It's a capability. Yeah, it's a capability. So I'll give you a famous example. Not famous, but within our industry. So it used to be long ago that the way that you protected a system, for example, that you told a circuit breaker when he needed to open and close, we would do with little computers that used only analog wires to send the signals around. And then when digital technology started to become available, we implemented our version of how we would do a digital software-driven ability to communicate inside of a substation. And our competitors did, and our other competitors did. Fortunately, very early days, the industry said, wait, stop. If we standardize the way that a circuit breaker should talk to a relay, or the way that a protection relay should talk to a user interface, then it makes it possible for the whole industry to move faster and to innovate faster. So at that time, we and all of our peers, all of our big peers, gathered over 20 years ago to build a special method of doing digital engineering for the communications and control of power systems. And that's known in the parlance. Well, unfortunately, we didn't come up with a sexy term for it, but it's known as IEC 61850.
Love, catchy.
Yeah, very, very catchy, very catchy.
So bringing so many systems together, that must be a bit of a challenge when it comes to cybersecurity.
It is. And it's both a plus and a minus, right? So where having interfaces, digital interfaces, makes it more secure is that when we are going to combine two systems together using a standardized interface, we can test that interface long before the system is ever deployed. So imagine it would be that we have two pieces of plumbing. We know that they're going to plug together, and we've tested back in the factory that plumbing's not going to leak. Then we don't have to worry when we assemble it on site that it's going to have to leak. So it makes it less likely that we've made a mistake in the piece of software that connects two software systems that would allow a hacker to get in. On the other hand, once we standardize the way that we connect systems, we also then publish to the world, by the way, this is the way we're going to connect systems together, which advertises to the black hats as well. What are the points of connection, or in this case, the points of interface that might be exposed as a way for them to get into the system? How do we make sure, we test within an inch of their life every interface that we use, that we publish, so that they are perhaps the most robust portion of any system is the points of connection between them.
And in our business, in the power grid business, so we need our power stations to run reliably. And these interfaces then come in and help achieve that. And you've mentioned circuit breakers, how digital can help. When you're looking at something as big as a substation, powering a whole city, how can a digital substation make the grid run more efficiently?
The first thing that they can do is by using interfaces which leverage digital technology. When we're leveraging digital technology, we as the electric power industry can become the beneficiary of some incredible technology used to build and drive the internet and all the business systems that are behind it, right? So we now can take control action with a higher level of redundancy and separate the brains of the system in a distributed fashion, so that we have many more options for where we deploy it, meaning that the operator who's running the grid can sit thousands of miles away from the circuit breaker, but be connected to it in essentially real time. and we can take control decisions in milliseconds that will allow us to keep the grid completely reliable. We can only do this with digital technology. We can only make sure that it's going to be fast enough and reliable if we use standardized and well-tested interfaces to do so.
So with different systems and different competitors coming together with different solutions as part of their product portfolio, there has to be some fragmentation at some point. How do interfaces deal with this sort of siloed data that there may be?
Yeah, it's a good question. So one of the things that we as an industry have seen is you need a certain amount of innovation to occur. Innovation allows the expression of new ways to do old things, right? Which ends up with fragmentation. It's a bit of Darwinism that occurs, right? Because the technologies that are extremely popular in one segment find their way to another. The old ones die out, right? And so, not every technology that we've adopted in our industry has lived and survived. Some of them get quickly deprecated. It's a bit more of a challenge for us in the power industry than it is in consumer electronics, because when we put a system into the field, it has to live for 20 years, right? That's the typical refresh rate for a piece of digital technology in the grid. The benefits, though, for allowing this innovation are great because they eliminate the silos of information, because without easy ways to exchange information between systems, what you end up is the system that collected the data tends to keep the data. And digitalization and having good means of sharing data between systems means that data collected for one purpose can be used for something completely different later. And this has really driven the application of industrial IoT, which is basically measure everything, keep all the data, and then we're finding uses for data that was collected 5 years ago on transformers and circuit breakers. That information collected then now helps us analyze where the grid is having problems, failing, and ways that we can design our equipment more efficiently for the future.
And now as well, with our knowledge of digital and how far it's come, substations must be designed differently. And, protection systems as well must be enhanced with the digital solutions that we've come up with. Would you say that's a fair assessment?
It is. So previously, building a substation and the way to implement the control and protection systems for the substation was a little bit of an art. And we found that many of our customers had their own practices and their own design practices to do more or less the same thing. And it worked, right? But it meant that an individual wanting to move from one customer to a different customer for a job, had to relearn how to go work in the kitchen, as it were, right? With digitalization, this has led to better practices, better tools that allow for the construction, the testing, the simulation of a system, so that what our customers tell us is that the amount of time to engineer a system today using our products and services, and those from our competitors as well, is significantly reduced to where it was just a few years ago. And it can all be manifested not as a set of drawings about what's going to be built, but in computer files that can be simulated and tested in the framework of a system digital twin, right? So that we can know well in advance before the system is deployed in the field, we can simulate exactly how it's going to perform.
So these interfaces that we've been discussing and digitalization sort of thrown in there for good measure, can we make a connection to how often they need to be maintained? So how often would you need to look at an interface and update that specific software? Is it something that when you go to a customer, you've got a specific set of time? Is it every 3 months or every year? But you need to check that the software is still behaving as it should, or it's been updated?
It's a careful balance, right? Because when we apply a piece of digital technology to a piece of what we call primary equipment, like a transformer, for example, we have to be cognizant of the fact that we're dealing with some extremely reliable hardware. And what you don't want is that the maintenance of the device itself is every 3 months we have to go change a little piece of software that monitors the device. It's important that when we implement an interface, especially an interface between a piece of digital apparatus and the underlying control equipment, is that it not change too often, right? So typically what we see is when there are cybersecurity issues, right? These interfaces and all the software that we deploy, will often be strengthened, hardened, or patched in order to resist. These are mission critical. But other than that, more or less, a well-performing interface should last 5 or 10 years before it needs to be swapped out. For example, we went over 10 years between the first industry release of 61850 version 1 and then to get us to the new one, which is version 2, which is much more powerful. It defines not only the vocabulary for the way systems should talk to each other, but literally how their behavior should perform. That was a major upgrade. It was carefully considered, carefully voted on by standards bodies, but now forms the basis of what we do.
Looking ahead, and this will be my last question for you.
Okay.
What do you think the future holds for software and hardware coming together?
Yeah, the overall goal, it sounds trite, but it's true, is plug and work, right? So what we really aspire to is our ability to build a new innovation on a piece of equipment, such as a power converter, for example, and be able to deploy it to site and have it interface with whatever control system is there, whether it's the digital brain supplied by Hitachi or that of our competitors, and literally have it plug and work so that all of the information flows in a secure fashion straight out of the box. Our customers want this because then they don't have to get scared of an upgrade or a replacement. They would be able to mix and match elements of their system and let it grow in an economically sustainable fashion. And of course, we as Hitachi Energy like this because it means that the faster that we can innovate, we can go to our customers that already enjoy our equipment, and we don't have to worry so much about backwards compatibility. So plug and work for us is the goal.
Thank you so much for coming in today. It's been
thank
wonderful
you so much.
chatting with you. Thanks for your time.